Again, my name is Jerry D'Antonio, and I'm here I work for a company called VHT, formerly Virtual Hold, and we're out of Akron, Ohio. Now, I've learned from my new friend, Ben, that if you've grown up in the Pacific Northwest, you might not know where Ohio is. We're going to have a brief geography lesson. Ohio is that really big state out east on Lake Erie between Pennsylvania and Indiana. Ohio is the 7th largest state in the Union by population, having a population about 25% larger than Washington and Oregon combined. Ohio is also the state in the Union that has the most metropolitan areas. We have 8: Cleveland, Cincinnati, Columbus, Youngstown, Toledo, Akron, Canton, and Dayton. And also, every 4 years, Ohio becomes the most annoying state on the planet to live in because we have 18 electoral college votes and are always a swing state. So, but you guys didn't come here to learn about geography or learn about Ohio. You came here to learn about concurrency. All right, so that's what we're going to talk about today's concurrency. At VHT, we are a Ruby and an Erlang shop, and concurrency is what we do. So today, the word for today is asynchronous. All right, so make sure you're all paying attention. I hear everybody say that. Say asynchronous. Asynchronous, right. Back in the prehistoric era, back when Mondo and I were young programmers, we did concurrency through locking and synchronization. You spawn a bunch of threads, you put locks on a bunch of resources, and then let them fight for those resources. There's a litany of reasons why that's really bad. Right? But today, modern concurrency practices all revolve around the idea of asynchronous concurrency. Instead, you send off a bunch of independent operations to happen, and then you coordinate them later on. Okay? Now, a lot of these modern practices are being incorporated into the standard libraries and languages themselves of most modern languages not called Ruby. Right? So to borrow an idea that Davey talked about earlier this morning, we're going to, in this session, learn about concurrency by looking at what other languages are doing and see how we can apply those concurrency practices in Ruby. This is going to be an extremely code-heavy presentation. I was going to say there's going to be enough code to make Aja happy. So much code, in fact, that if I took Ryan's 10 extra minutes from yesterday, I still couldn't go into the code in detail. So what I've done is I tweeted a link to the Cascadia Ruby hashtag of the Git repo where all of this source code is at, along with the slides and extensive notes. So I'm going to go through these things fairly fast and like everybody just focus on the concepts as we go through these things and not get into too much detail of the code right now. Okay? So I'm going to divide this into 3 sections. First section, I'm going to talk about a bunch of concurrency abstractions that are popular in functional programming language today, mostly Clojure, Erlang, with a little bit of Scala thrown in. The next 2 sections, we're going to look at major concurrency paradigms around which you can design entire applications. We're going to look at the event-driven model, and we're also going to look at the actor model. So with that, let's get in and start looking at the code. But first, we need Crashtestdummy. When looking at concurrent code, oftentimes you just throw these sleep statements in as a way of saying this thing's taking a lot of time and that thing's taking a lot of time. For this presentation, I put together a piece of test code that exhibits a couple of important characteristics regarding concurrency, and we're going to use that test code over and over and over again. So we're going to look at that first. All right, so this is the test code we're going to use. This horribly designed class here does actually exhibit a couple characteristics that are very important to us. What this thing does is you create a new object, you pass to the constructor the name of a corporation that is traded internationally, Yahoo, Microsoft, Google, Apple, something of that nature. Then when you call the update method, it's going to go out, it's going to hit the API, and it's going to bring back information about the stock ticker symbols that that company uses on all of the international stock exchanges. We're then going to tear off all the garbage Ajax-y stuff that they surround the data in and store that information in an internal array. Now here are a couple things that are important about this. First off, this thing does blocking I/O. All right? Blocking I/O is one of the main reasons why we'd want to write concurrent code. So that's the first reason why this is good. This has 2 things about it, however, that are very bad. How many people have heard that shared mutable data is bad? All right? Whatever you heard is not correct. It is 10 times worse. Right? Shared mutable data is bad. This particular class, in a somewhat typical object-oriented fashion, represents shared mutable state. Not only does the state mutate when we call update on this thing, but it also exposes a reference to a mutable object, which is that internal data structure, which are both very bad things for concurrent programming. So we're going to use this as our test example in all of the code we look at and talk about how these different abstractions we look at can help us avoid some of the concurrency problems that this thing represents. Okay. So the first concurrency pattern I want to talk about is called the future. Future is one of the 2 core concurrency constructs in the Clojure programming language. Future is very pure. It does one thing, it does one thing very well. A future represents an operation that returns a value and occurs at a future time. It's that simple. You take some operation that's taking a long time, you throw it out there on a different thread, and you say, go do your thing, and I will come back, and later on, I will get the value of that operation. Okay? So this code, for the first section, we're going to use as our example a gem that I put together. It's available on GitHub. It's, you can get it from Ruby Gems. It's something that we use, it's called concurrent-ruby, and it's something that we use at VHT. All right? This gem incorporates some of what I consider to be the best asynchronous patterns available today in other languages, all implemented in Ruby and all usable in your code. This gem has no external dependencies, has no conflicts with any known other gems. Everything's very simple. Everything is very targeted, does one thing well. Everything in there is ripped off from some other language, and it runs equally well on MRI and JRuby and Rubius. So we're going to use that library for the first part of this presentation. So right here, this code is very straightforward. We're going to create a future object. We're going to say, go off and perform this operation. And that operation is to do that update we looked at a minute ago. All right? When you create a future, it has 3 possible states. Future starts out in the pending state because the operation is not yet complete. When the operation completes, the state changes to either fulfilled or rejected. If the operation succeeds, it becomes fulfilled. And the value property of the future holds the result of that operation. If the operation throws an exception, it becomes rejected, and the reason property holds the exception that was thrown. Very simple. You send this thing out there, you say, go do your thing, you do important stuff, later on you go back and say, what was the result of the operation? Did you succeed or did you fail? Okay? It's very straightforward, very, very useful, and like I said, this is one of the core constructs from Clojure. Now, whenever you're doing asynchronous concurrency, there's a good chance you're going to want to know the result of the operation. And there's 2 ways you can do that. One we show here, we're going to query the object and say, what was your result? The other way we can do this, if you're a JavaScript programmer, you're very, very familiar with this, it's the idea of a callback. We can say, go do this operation, and when you're done, run this other piece of code. All right? Ruby, the standard library, provides us with a very usable, very serviceable callback mechanism called the observable module. So in this case, future, in this particular implementation, supports the observable module. So in this case, we're just going to create a simple observer class. The update method in that observer is going to receive as its parameters the time of fulfillment of the future, the value of the future upon completion, and the reason, one of which of those 2 values will always be nil, because I succeeded or failed. And it's that simple. We just create the object, we say go off and do it, and then we call add observer. Now, I want to make a very important point about concurrency here. Something that, line 18 on this code. It looks very innocuous, but it's a very, very important line of code for this reason. All of the concurrency abstractions we're going to look at today are going to try and hide the internal details of the concurrency. You're never going to see thread.new. You're never going to see mutex.synchronize. But we are still operating in a concurrent environment, and we can never forget that fact. That completely innocuous line of code right there, however, could be problematic because there's no guarantee that the future is going to complete after we add the observer. Remember, concurrency is non-deterministic. We have no idea when things are going to happen. In theory, because we're sending a long-running operation, add observer will happen before the future completes, but we can't guarantee that. Now, in this case, this particular library is smart enough to recognize that, and should the future complete first, that add observer method will work the way you expect it to. But a word of caution, no matter how much we hide the internal details of concurrency, remember, things are still non-deterministic, and you can't ever forget about that. So this is future. The next mechanism we're going to look at is called the agent. Agent is another core concurrency construct from Clojure. And one of the things that's fascinating about the agent is it represents the one thing I just told you never want to do. An agent actually represents the idea of shared mutable state. This is a fascinating construct because it does something that's very unique. Back in the old days, the way we would handle, let's say, the score in a video game. You've got this score, you got a bunch of things going on in different threads, and everything wants to update the score. All of those threads would have to lock that score in order to be able to update it. And every time one of those threads tried to lock it, it would block all the other threads, and you'd have all this contention. What an agent does, and this is really fascinating, it says the agent represents a value. But instead of modifying the value, you are going to send to the agent an operation to be performed against the value, and the agent will then queue up those operations and perform them one at a time. And anytime you request a value from the agent, it'll be what the value is at this time, regardless of what's been queued up. Here's a very simple example. We're going to create this agent. We're going to give it its initial value of an empty array. Okay? We're then going to go out and we're going to say, we're going to create one of these new finance objects, and we're going to send the operation to the agent and say, go update your internal state with this operation. We send the operation against there. The nice thing about this is because we're sending an operation, we're not actually operating directly on that value. Our operation doesn't need an a priori knowledge of what the value is. All right? When that operation runs, the agent passes to that block the current value. We then operate on that, pass back the new value, and that becomes the new value of the agent. All these operations come into play and they just get queued up. They run continuously in order, and anytime you request the value of the agent, you get whatever the value is at that moment. This particular implementation of agent also supports the observable interface. So what you could do, if you think of that score example in a video game, what you could do is you could have an agent representing the score, an observer whose job it is to update the score on the screen, and all of the different threads that want to change the score just start throwing these operations at the agent. The agent processes them in order, and then whenever one of those occurs, the observer gets notified, the screen updates. We now can have that running score total without ever having to block any of our threads. Right? So now, this code really accurately represents the agent very well, but you should also note that this code is horribly, horribly, horribly bad and wrong. And if you write this code in production, I guarantee you one of the worst debugging sessions you're ever going to have. So take a look at that for a second and try and see if you can spot the problem with this code. It's not with the agent itself, it's with how I use the agent. All right? Remember, in concurrent programming, mutation is bad. Shared mutable data is bad. And if you look at that code, every time you requested the value of the agent, we passed back an unguarded, unthread-safe reference to a mutable data structure. Every thread that has access to the agent can now grab that thing, modify that thing under the hood of the agent, and wreak all kinds of havoc within your program. Right? So it's really bad. How do we solve that problem? Well, in functional programming languages like Clojure and Erlang and Haskell and others, they have immutable variables. The idea is if you're never passing around immutable reference to anything, then you can pass these things all around all the different threads as much as you want. That's great, but it brings about its own problems. The thing is, in Ruby, we don't actually have immutable variables, and we never will, probably. So you always have to be aware of that mutability. So what's one way we can solve this problem? Well, the best way to solve this problem with the given example is with a hamster. Right? Nobody saw that coming, right? In 2000, a guy named Phil Bagwell wrote a research paper about something called fast indexing through a data structure called a trie. Later that led to another paper by Phil Bagwell about something called ideal hash trees, which are incredibly fast data structures built off of basically like a binary tree, but with at least 256 nodes hanging off of every other node. Incredibly fast operations up to 1 million objects in the tree, because you'll have to go down 3 levels of indexing, right? Ideal hash trees later on became the internal mechanism underneath Clojure's data structures. Right? The language Clojure is functional. It has completely immutable data structures and incredibly fast operations of those data structures, and it has that because of this thing called an ideal hash tree. Well, in Ruby, fortunately a couple of Rubyists read Bagwell's papers also and created for us in Ruby an ideal hash tree implementation that gives us immutable, thread-safe data structures that are also extremely high performance, exactly the same thing going on internally in Clojure, and they call that gem hamster. So in this example, we're going to use the hamster gem for our internal data structure. We're going to use a hamster vector, which is basically array, but it's immutable. So as we go through these operations, rather than modifying the array in place, we have to always return an updated reference to that vector. That's not a slow operation because of those ideal hash trees. This is actually very fast. So now we've taken that example, and by using hamster, created something that is thread safe, immutable, and now whenever we request the value of that agent from another thread, we get a copy of the agent, of that vector at that point in time. Not only is it thread safe, but it actually represents the data at that point in time. So using Hamster, we've been able to take a very complicated mutability problem and solve it completely in the same way you would solve it in any one of the functional programming languages. Now, real quickly, the second example I want to show you is a library called ThreadSafe. ThreadSafe is written by one of the members of the JRuby core team. It's a great library that provides us fully thread-safe arrays and hashes. It's definitely a library that you should look at and you should consider using your concurrent code. But I wanted to show this example that in this case, even though we have thread-safe access, we still haven't solved the problem because we were still returning a mutable reference. Okay? Thread safety is good, immutability is better. All right, so having looked at those two, I want to quickly go through a couple other of the mechanisms in this particular library so we can move on to those other two topics. Remember I said this particular library was designed to be a utility belt sort of library. So there's a whole bunch of other abstractions in here. If you're a JavaScript programmer, you're probably familiar with a promise. Okay? A promise is like a future that we saw earlier, but it's chainable. A promise begets a promise, begets a promise, begets a promise. Okay? There are rules about how you handle rejection and acceptance along that chain. This particular implementation, one, shares a lot of the API methods that Future does, but it also is conformant to both the promises A and promises A plus specifications. Okay? This is a TimerTask. You actually saw this yesterday. The gentleman who did the robotics demonstration used a TimerTask in Java in order to look at the state of the UI and every time, few times a second, send that state across JRuby to the LED and make it work. So TimerTask is just what they showed yesterday. This is a pure Ruby implementation. Say, I want this thing to occur at regular intervals. Just go off and do it. And it can be stopped at any time. Okay? We're going to talk more about actors later on in the presentation. But this is an actor implementation that is based upon Scala's actor trait in the Scala standard library. And we'll talk more about actors later on, but this particular implementation here was actually taken from a Scala tutorial on how to use actors. And this is a ping pong program that represents, that does the exact same thing as that tutorial. You can get this, the URL for that Scala example is in the notes. Okay? This last thing I want to show you, this is actually my favorite code example in the entire presentation. How many people have heard that Erlang is incredibly fault tolerant? Up to 9 nines fault tolerance, right? You may have heard let it fail. The way Erlang accomplishes that isn't so much through any magic of the language itself or of the virtual machine, but because of a design philosophy called let it fail. And within that design, you have something in the OTP, which is a standard library called a supervisor. We'll talk more about supervisors later on, but the supervisor is the magic in Erlang that makes things fault tolerant. The supervisor manages other processes, and when those processes die, Erlang, the supervisor restarts them based upon a restart strategy. This supervisor implementation here is a functionally complete implementation of Erlang's supervisor in Ruby. It's implementation agnostic, so you can send any object to this to have it supervised so long as it supports 3 methods that are documented in the README. So what we're doing here is we're going to create a couple of actors. We're going to create an actor that basically, when given this query, goes out and gets that data that we've talked about before. We're going to create a pool of actors. All right? We're going to create 5 actors that will load balance across a common mailbox. So basically, we can send requests to these actors and load balance across 5 of them. We're then going to create 2 timer tasks that say, send these messages at this random interval to this pool of actors and let them handle the result. We're going to add them all to the supervisor and tell the supervisor, add these workers, manage them, make sure they keep running, handle their life cycle, all that kind of stuff. We run the supervisor. When we run the supervisor, a few seconds later, you're going to start seeing all this stuff start flying across the screen as those timers start to run, send those tasks to that actor pool, and have actors respond. Eventually, we type stop. It's called the stop command of our supervisor, and it shuts everything down. Okay? That right there is the same kind of thing you can do with Erlang with the same level of fault tolerance and reliability, all done in pure Ruby and available to you today. This library also includes thread pools based upon Java, as well as a couple of other utilities. So, like I said, this library, this gem, you can pull down, put in any code you have, and it should have no conflicts, and it should allow you to start adding some concurrency to your code. All right. Now I want to move on to 2 different paradigms around which you can build entire applications. All right. The first one we're going to look at is event-driven programming. Do we have any Node.js programmers here? All right, you've all done event-driven programming. Do we have any JavaScript programmers here? You've all done event-driven programming as well. Any event-driven programming environment is based upon the reactor pattern. The reactor pattern was first documented in 2000 in the book Pattern-Oriented Software Architecture Volume 2, Patterns for Concurrent and Networked Objects. The reactor pattern requires three things. You have to have the reactor, then you have one or more demultiplexers, and one or more event handlers. Here's how this works. The reactor runs in a continuous loop forever and ever and ever and ever. That's the event loop in JavaScript. Just runs forever and ever. The demultiplexers listen to your event sources. And when an event comes in, the demultiplexer takes the data from that event source, like TCP connection, RMI connection, something that way, something like that. Demultiplexes it, passes it off to the reactor. The reactor then looks for an associated event handler and calls the event handler code. The event handler code runs, and the reactor continues going on and on and on. What makes this work, this is good when you're listening to event sources and you have a lot of blocking I/O. The reactor runs on one thread, but all the blocking I/O happens asynchronously on other threads, so the reactor can continue going round and round and round and round. So Event Machine is a reactor-based, event-driven gem that we've had available to us in Ruby for several years. It actually slightly predates Node.js, and it provides that capability for us. This is a very simple example. In this case, we're going to use as our demultiplexer the built-in simple server demultiplexer that allows us to listen to bind to an IP address and a port number. And the event handler is going to be this echo class. Everything in an event-driven model is an event handler. And there are a whole bunch, and every demultiplexer provides different lifecycle events. So this particular demultiplexer gives us a lifecycle event for post init. When a connection is made, run this code. It also provides us with a receive data event. Whenever data comes across the connection, run this code. So what's going to happen here, the important thing is on line 20. Line 20 is where we start the reactor. Event machine.run. Now remember I said the reactor runs this continuous loop forever and ever and ever and ever. This is an important conceptual thing to get across. That block is not the reactor loop. That block is an initialization block. When you call event machine.run, you pass it a block and you say, this is how I want to configure my reactor. The run command, the method, actually blocks forever. Your code will not go past line 22 when you run this until you explicitly stop the reactor. So we start the reactor, we pass it the initialization block. Everything in that initialization block is our application. So if you notice in the telnet session in the top right, I telnetted into that. I got the post init message back. I started sending messages over. That triggered the receive data. The send data message on line 14 actually comes from that demultiplexer as well. I just bang some messages back and forth, and then when I send stop, I call stop on the reactor, which stops it. At that point, event machine.run ends, and we get to line 23 and everything goes. Okay? So that's a simple example. Just to give you a sense of the power, let me show you a much more contrived but very complex example. In this case, we use Event Machine extensively at VHT. We're big, big fans of this because of the AMQP gem, which allows us to create workers that listen to RabbitMQ. So what we're going to do here is we're going to initialize a much more complicated example. In this case, we're going to use AMQP to listen to RabbitMQ. We're going to use the simple echo server we saw before. We're going to trap a couple of signals so that we can Control-C out of this thing. We do Control-C, it'll shut down the reactor. And the last thing we're going to do is we're going to use this thing called Arachne RPC. Again, the robotics guys yesterday showed using JRuby to do RMI calls across the network to another, their device. Arachne RPC is basically the same as JRuby, but it's designed to be event machine friendly. So we fire this thing up, the reactor listens to a whole bunch of these different things, and then responds to all these different events. Okay? Very, very powerful. But you'll notice when you're using event machine, it takes over your entire program. When you decide to go with this direction, it's really, really powerful, but it takes over the entire program. Now, one word of caution, whenever you're using any kind of event-driven programming, whether it be event machine or not, and that's this. Do not block the reactor. Right? That reactor loop runs forever and ever and ever on a single thread, with the expectation that all the event handlers and all the blocking I/O are going on other threads. If you do blocking I/O on the reactor thread, what's going to happen is you're going to block the reactor and prevent it from responding to other requests. Okay? Our finance class does blocking I/O, right? So when we run that thing in an event handler, we're blocking the reactor. There's two ways to avoid that. First, you can find a library that is event machine friendly. In this case, we've replaced REST client with EM HTTP request, which is event machine friendly. And in this example, we are actually going to wrap that synchronous I/O in an asynchronous call by using event machines deferred. Deferred is similar to a future, but it's built into event machines. So you say, go off and do this blocking I/O, but do it on another thread, and then we get the call back. All right? I'm running out of time, so I'm going to talk briefly about actors next. I'm going to have to go, unfortunately, you're going to have to look at a lot of this code online, and I apologize for that. The actor model has been around since 1973. It's actually surprisingly controversial, but, you know, we're programmers. Anything that's worth talking about is worth getting into ridiculous flame wars over. And the actor's method is similar. Actor's been around since 1973. It was originally proposed by Carl Hewitt and a team of researchers at the MIT Artificial Intelligence Laboratory. The idea behind an actor is every actor plays a role on stage. It only does its role, and then they all coordinate together in order to do the entire performance. There is no single universally accepted strict definition of actor, right? Because the original proposal was in 1973. Additionally, actor implementations across languages all look very different. All right? Even implementations within the same language look different. The actor in Scala standard library looks very different than akka. So in addition to the actors that were available in the library I showed you earlier based on Scala, Celluloid is a actor-based framework that exists in Ruby today as well. Okay, I'm not going to have too much time to go through this. The important thing to notice is that Celluloid fully embraces the idea of object orientation, and rather than taking the functional approach of sending operations off to other threads, Celluloid makes your objects fully asynchronous. Now, to do that comes with a lot of internal complexity. A way of, you have to be able to protect the data that's going on there. You have to, so that's why down here on line 33, we're calling an async update, which makes that update call happen asynchronously. So Celluloid is a very powerful library that provides you a lot of capabilities. And I'm sorry I don't have time to go through the code, but a couple of things to know about Celluloid. Celluloid is a comprehensive framework that is intended to be your one-stop solution to concurrency. That means that Celluloid stuff only works with Celluloid stuff, much like Event Machine did. Celluloid expects you to use only Celluloid stuff, and there's a lot of tight coupling between what's going on in Celluloid and a lot of internal complexity. Now that's great if you need all of the things that it gives you, but it does come with a couple of gotchas. In fact, there is an actual page on the wiki for Celluloid that talks about Celluloid's idiosyncrasies. And if you're going to use Celluloid, you get a lot of power, but you need to make sure that you read up on those idiosyncrasies and use Celluloid the way it's intended to be used, same as we did with Event Machine. So, to end this, here's my challenge to all of you. Write code. Concurrent systems do not work the same way as linear systems. They behave differently. They require different ways of thinking. They require different designs. They require different ways to debug. All right? You cannot learn concurrent programming simply by reading a book. You must write the code. All right? If you look over all the stuff we did in the past half an hour, we did a lot of incredibly powerful things, and not once did we ever have to type thread.new. Most of our code examples were less than 10 lines of code, and even the complicated ones weren't more than 30. There is nothing that I showed you today using these 3 gems that you can't go out and do today. All of this source code is in my GitHub repo, along with, like I said, the slides and extensive notes. I've even provided a gem file. All you need to do is grab it and start writing code. So that's my challenge to you. If you think concurrency is important, and you should, if you're curious about concurrency, which you should be, and if you think concurrency is something you want to learn, which it should be, write the code. Go out, open up your favorite editor, open up your console, git clone, bundle install, IRB, and start writing the code. Again, my name is Jerry D'Antonio. Thank you very much.